Good morning, ladies and gentlemen. I'm warmly welcome you to today's seminar on piezoelectric sensors. For most of you, are piezoelectric pressure sensors part of your daily work, and I suppose that you have already attended some expert-led training session and have been properly trained. As you can see from our agenda, today's webinar is not an actual training session. The goal of this training is to reveal information that is not usually included in such trainings. Of course, every specialized sensor handling training contains part about sensors, cables, how to connect them together, and many other important information. My job is to revive, or maybe just brush up a bit, all the information, wrap it together, and of course, add something extra. If you have any question during my presentation, use the chat. I'll do my best to answer your questions at the end of this webinar. If you are interested in a separate topic in detail, let me know in the chat. All your questions and or requests will be answered. So let's go back to the roots. Piezoelectricity is a relatively young field. The first demonstration of the direct piezoelectric effect was in 1880 by brothers Pierre and Jacques Curie, as it is usually stated, for example, in Wikipedia. Well, what is the piezoelectric effect? The piezoelectric effect is the ability of certain solids to generate an electrical charge in a response to mechanical stress. The applied force causes the microscopic structure of the object to change, resulting in dipoles between which an electrical field is generated. The piezoelectric effect is also reversible, meaning that piezoelectric materials undergo elastic deformation when an electrical field is applied. One of the most important piezoelectric materials are tourmaline quartz. What is not commonly known, however, is the future development of piezoelectric pressure sensors. The first publication on measuring piezoelectricity was made in 1919 by Sir Thomson in England. You can see the extract from the article from the June 1919. And the interest was focused on explosion pressures. As far as is known, the first successful application of piezoelectric pressure transducers was made at the Deutsche Versuchsanstalt für Luftfahrt in Berlin by Dr. Werner Göhlke in 1935. This type of transducer, called piston, this part is the piston, which operates very stiff membrane, and here you can see the crystals. And here this part is a preloading element. So the type of this transducer was called a piston design and was in use for about 30 years. It must be emphasized that these sensors were, let's say, homemade products. In other words, whoever needed them had to make them. No company produced piezoelectric pressure sensors. However, this changed after World War II. Next very important steps were done by Walter Kistler, very well-known physicist, inventor, and philanthropist. He obtained a patent for charge amplifier in 1950 and kick-started the expansion of piezoelectric sensor. You can see here his first commercial piezoelectric sensors, PZ14. And I can show you that the basic shape of sensors were not changed that much. Yeah, so this is quite old sensor, but still very new one comparison with this PZ14, and you see that the shape is very similar. Walter Kistler founded Kistler Instrument Company in USA in 1954, and later in 1957, Kistler Instrument in Switzerland. Since then, Kistler belongs to the leading company in piezoelectric technique. In 1958, a completely new, and from today's point of view, one of the most famous pressure sensor on the world was introduced. The miniature sensor 601, 601H, 601A, so on. And we can see here his bigger brother, a little bit, 701H. So it's very similar. The shape is similar, but the size is a little bit bigger. Yeah. After 63 years of production, our first miniature sensor has been replaced by a new generation. The same shape from outside, but modern technology inside. And this leads us to the design of piezoelectric sensors. Simply said, there are only two basic internal designs and two basic external designs of pressure sensors. Inside, the crystal can be in columns, like here, or on discs, which you can see here, the CT, the sensor, or here, the schematic. Housing type are front sealed, from the front side on the same side as the membrane, or shoulder sealed, which is here, shoulders a little bit far from the membrane. So these are, let's say, these basic designs. Of course, the shape of the sensor influence the mounting, the measuring conditions, and so on. So we already saw some shoulder seat sensors, like this one. And now, or that one, another shoulder sealed sensor. And now I show you the front sealed sensor, which is this one. So as I told you, okay, shoulder seal sensor has sealing areas here, and the membrane is here. The front seal sensor has a sealing area here. You can see on the CT this part, and this is the one ring around. Yeah. And here in the center is the membrane. This part is the membrane. So you can see here the membrane part. You can see that the membrane is quite complicated in comparison with this kind of sensor. Yeah, see the membrane is quite flat. Of course, you can combine the front sealing sensor with column design and the column and the shoulder seal design with the discs inside. It is not mandatory to just use the same column design in shoulder seal sensor and disc design in front seal sensors. Of course, the mounting influence the measuring condition. In the short seal sensor, you can see that the sealing surface is here and the stress goes up, and the crystal part is not influenced by the mounting forces. On the other hand, when here is the pressure, it goes all the parts, this one and that one, bounding in this direction. So you have to count with it and leave enough space here without any particles to allow the sensor to so-called breathe, moving this way and that way. So this is really just another disadvantage of this sensor. The shoulder sealed sensor, the front sealed sensor, as I said, it has a sealing surface here and here, and the membrane is here and it's acting like this. So the design of the sensor must be in the way that the mounting force goes directly through the sealing surface to the nut and do not touch the membrane itself. So that's the reason why the shape of the membrane is so complicated. To allow all mounting forces goes directly to the nut and do not touch the membrane. From the point of view of an airbags, squibs, inflator, and gas generators testing, we recognize just only a few types of piezoelectric pressure sensors. So we have here 6217 family, which was originally designed for airbag and squib sensors, or let's say easily automotive explosives, which is this sensor. Okay, this sensor is a M12 sensor, quite robust. You can split it to two parts. This is the measuring element, and this is the mounting adapter. And this mounting adapter can have different connectors. We have here 1032 connector, but you can have on it even the so this is 1032. This is a BNC connector, and this one is a TNC connector. So you can just replace the top part of the sensor and have more connection variability. Yeah, so this is the only sensor which was specifically designed for automotive explosives testing. Second, very, very popular sensor is a 60-15 sensor. It's a sensor M10, and you can see here the sensor. It's a little bit smaller. Again, front seal sensor, very popular sensor. Again, with the swivel nut. The swivel nut can be removed and replaced if it is, for example, this hex nut is damaged, and you can replace it very simply. So this is the 6215 sensor. This is the standard one, and this is so-called short version with built-in cable inside the sensor. So we have these two front seal sensor, very well known. Next one is one of the very, very well known around, not only in automotive explosive field, but everywhere in testing. It's a 601C or 603C sensor. I already showed you this sensor, so this is the basic short version of the sensor, or we can have now in the long version. So these are very popular small sensors. Okay. Last but not least is the sensor 6213B. This is a very, very robust sensor. Again, M12. It's a one-piece sensor. You can not separate the nut with the threaded nut. So you can see here the welding. You can see the welding here. Membrane, you cannot separate this sensor in two pieces. This sensor is 10,000 bar sensor and dedicated for calibration purposes mainly. All right. So a little bit more about technical parameters. As we already said, the 6217 sensor, it's a sensor which was designed especially for automotive industry, and it has variation with different swivel nut, different connectors, can be 1032 BNC or TNC. As you can see here, the connectors different connectors. The design is up to 2000 bars, which should cover majority of all automotive explosive testing. Very, very sensitive sensor, 13 picocoulomb per bar, and with excellent linearity. Second front seal sensor is a 6215 sensor, which has only one possibility. It is a KIAC 1032 connector, and because it designed up to 6000 bar, which is far away from the automotive explosive range, so that's the reason why the sensitivity is low. This sensor was originally designed for ammunition testing and was launched in 1982. The sensor 6217, it's quite new. It was launched in 2017. So you can see there is some technological step ahead. The last sensor 6213, as I said, this is sensor very robust, very nice sensor, very precise sensor, and it's rated up to 10,000 bars and with really excellent linearity, and its sensor is used mainly for calibration purposes. So it was about front sealing sensors, and we can skip to the shoulder seat sensors. So we have, let's say, two variations of the 601C or 603C, depending on the maximum pressure. So 603C and the 601C has absolutely the same outer design. There are no differences. The differences are only in internal design. So one is rated up to 603C is rated up to 1000 bars, has a nice sensitivity, about 5 picocoulomb per bar, and has very, very good vibrational performance. It can be produced like standard piezoelectric sensors or with IEPE output. There is a built-in electronics, which is fed by current and generate some voltage. Same sensor, same design, but different internal design is a 601C sensor. It's rated up to 250 bars with very, very high sensitivity, which is 37 picocoulomb per bar. So you can measure very precisely in the range of small pressures. You can see the linearity of the sensor is excellent. And again, it can be directly only with piezoelectric. That means a charge output or IPE output, or let's say ICP. So these two sensors with the same housing for different pressures. The 601C has very, very good thermal performance. Thermal performance, yes, but what does it mean, thermal performance? Okay, let's go ahead. What is it? So the thermal performance is the behavior under high temperatures or different temperatures or very low temperatures, high temperatures, depend on the application. In our case, it's automotive explosion. We are talking about high temperatures. So what does it mean? Here we can schematic sensor and mount it in mounting board. So it means that the heat flux goes through the sensor, through the membrane, and here in the sealing part, there is a connection, direct connection between the sensor and the mounting board. The heat goes out. So this is something which we cannot avoid. It is there all the time, and I can show you what happens when the sensor is exposed by high temperature. So I prepared here okay, I prepared here a experiment. So we can connect to the channel number 2, or channel number 1. Okay, of the oscilloscope. This oscilloscope is connected to the charge amplifier, standard Kistler charge amplifier. You can see here. And to this charge amplifier, we are going to connect a sensor. We can use, for example, this sensor, connect. And that's it, connected. Now we start measure, and we can see we have some signal. Yeah, with some noise, so on. Can stop the measurement. Okay, this is the standard conditions when the sensor properly measures. Now we prepare hot water, a lot of steam. This, so I start it, and we have to a little bit wait. Going to happen. Oh, okay, it's going to start boiling. So we press measure button, and now I immerse just to the steam, and you see the immediate effect of the sensors. The signal went down. Okay, so this is so-called thermal shock, and you can see that any sensor can survive without some effect. And the level of the effect depends very much on the application, the heat flux going through the sensor. Very depends on the application. What happened during the thermal shock? Why it's there? So normally the pressure increases very, very fast, and it's usually the speed is about the speed of sound. So first, the membrane of the sensor is touched by the pressure. Then, after a little while, the heat flux touch the diaphragm of the sensor. And what happens when it is touched by the very hot environment, hot gases? There is the very tiny part of the membrane is heated very fast, and it means that this is much more elongate than this part of the membrane. So this part is shorter than that part, and it causes that the membrane change its shape in this way. So that's the reason why we saw the decrease of the signal, like decreasing of the pressure. So the pressure signal is very fast with the speed of sound, and the thermal flux is slower than pressure, and I would say unloading the quartz element. This quartz element is unloaded by the deflection of the diaphragm. You can see it here on the diagram. The blue one is the peak pressure at the peak trace, normal peak trace without any influence by the thermal shock. Here, the violet part is the combustion flux. It's a heat flux. Yeah, not combustion, heat flux. So pressure is very fast. So it can reach the peak pressure without any problems. Then comes the heat flux and start influence the pressure curve. And that means the pressure curve falls down faster than it should be and measure lower values than it should be. And of course, it can be under the zero. So depending on the application, the thermal shock line can be negative or positive, I would say. So you can find it here or here. It depends on the application which we have. Usually, thermal, if it is high temperatures, we have a negative values here. If it is low temperature, below zero for minus 50 degrees C, we can reach this curve. That means positive impact. So this is something what we do not want to have. How to avoid this membrane deformation? We have to go back again to the different designs of the sensor. So first, it was shoulder shield sensors, and the shoulder shield sensors can be covered, or the membrane of the shoulder shield sensors can be covered by something which protect the membrane. So it can be our 1033 grease, or it can be a Kapton foil or high vacuum silicone, or the best one which we can offer is RTVs, so-called the room temperature vulcanization silicone. And I can say that it is unbeatable in thermal shock reduction. It is very easy to apply. We can even deliver some tools how to help you with applying. But it is really, really good. Even the preparation of the sensor takes a little bit more time than just glue something or put some grease on it. But the performance of the sensor is excellent with the RTV. So I show you how to apply the grease. It is a very simple way. Okay, ups. So it's here. Well, so we have a sensor. I use this bigger one, shoulder sensor. We have here the grease, 1063, and we can put on it slide coverage. Well, and that's it. Yeah, it's, I would say it's a first aid. If you do not have anything, you see the influence by thermal shock, you can try this. It helps, but not so good as the RTV. On the other hand, I have to say that thermal shock barrier lowers the natural frequency and even may affect acceleration sensitivity. And because the layer of the RTV is the biggest, it means that the layer influence the sensitivity and other parameters of the sensor the most. Of course, all these tools for reduction of thermal shock must be tested properly for every single application. Of course, even the mounting position of the sensor must be taken in consideration. It is strongly recommended to use for the manufacturing of the direct flash mounting board to keep exact dimensions and really use recommended tools for that. You can see here on the picture exact dimension which must be kept. Especially as I mentioned before, this part is very important to have enough space between the sensor and the mounting board for so-called breathing of the sensor, and on the other hand, avoid particles to enter. So what we can recommend to use is to buy with a sensor appropriate adapter. So this is the adapter M10, and here is the for the 601-3 or 601C sensor mounting adapter, which is properly machined and guarantee proper functionality of the sensor. For the small sensor, you have even the extension just for easy mounting, like this. Yeah. Or, of course, for these long sensors, you have a swivel nut here, which can be used. Yeah, that's it. It is really good to use original adapters, not only for here. So this is about shoulder shield sensors. Front shield sensors has different possibilities. Front shield sensors can be fitted by some caps or protectors. You can see here some caps or thermal protectors, which are inserted inside this protector. And I show you on the video 2 ways how to protect the sensor against the thermal shock and against high energetic particles. So we have 2 ways how to protect the sensor. First one, it's according NATO standard. The sensor, this is the 60 to 15 sensor, this is the cap, so-called diaphragm protector, and 2 sealing rings. Of course, you need the lubrication grease 1032, and if necessary for the cleaning, the spray. Visual inspection of the sensor, use all the time only good sensor without any scratches and damages. You apply a little bit of the grease and insert the sealing ring all the time by the proper direction. Then insert the cap or diaphragm protection. Again, apply the grease and add second sealing ring. So that's it. It protects against thermal shock and against high energetic particles. Second installation is a little bit more complicated, and you see that the shield has 5 holes, and you have to put in the central hole the thermal protective plate. The rest is the same. Again, lubrication grease. Add the sealing ring. And now you have to prepare the protection shield with the protective plate. Then put inside the sensor. And add last sealing ring. That's it. All right. So it was the protection of the sensor against thermal shock. As on the shoulder shield part, we discussed about the mounting board. Now we have to see the importance of the mounting board or of the quality of mounting board for front shield sensor. I'll show you another video where you can see how to check the mounting board and if necessary, how to repair. So for visual inspection of the sealing surface, you see the scratches down. So this is not allowed and you have to remove these scratches from the sealing surface. So you apply the grease on the reaming tool, a little bit on the thread for easy installation. You have to mount very slightly by 2 hands, then put hexagon part, tighten slightly by 1 hand and turn by second hand. And after, let's say, 10 turns, you see the particles are kept in the grease and did not remain in the mounting board. So this is the result of our work. Yeah, so this is how clean and nice must be the mounting board. Well, last not but least is a cable, an integral part of every measuring chain. So, cable, of course, but not just any cable. You need the right cable for the right results. And in our case, the right cable is the high impedance and high quality cable, which is in good conditions. So, the cable design is a little bit complicated, not easy. This is very thin cable. It's 2.5 millimeters only. And the cross section looks like this. So on the top, the blue one is the outer insulator. Then after that, we have a electrical shield, which is from the backside covered or coating with a conductive graphite. And then here is the electrical insulation and inside is the inner cable. So you can see here the cable 1032 connector and BNC connector here. And of course, I show you the cable in reality. So this is the real cable. And all the time you should store the cable like this with all the caps, covers. Both connectors are covered. And the cable is all the time protected somewhere on the safe place, not to be damaged. But every single cable has connector, and our sensor connector, which is 1032, is quite complicated, and to produce this connector is not simple way. As you can see here, it consists from many parts. Yeah. So you have to keep the connector all the time covered and be very careful how you use the cable and what you do with the cable. So all the time we use the sensor for charge. That means this cable must not be dirty with a grease or oil, and you have to keep it in a safe environment to be sure that the internal insulation resistance is greater than 10 power 13 ohms. I can show you simply how to measure, how to be sure that our insulation resistance is still good enough. We have a special tool, which is this handheld, battery handheld. You can start the measurement. Here is the cable, so we can just connect the cable. You see that the resistance went down, dropped down, and we have to wait until the result is measured. So the red means poor, the yellow means so-so, and the green area means good quality. So this sensor, as you can see here, has even higher sensitivity, resistant than 10 power 13. So this cable is in very good condition. So what to do to ensure the longevity of your cables? What to do? Keep the measurement right? The answer is really very simple. Clean. Clean sensor connectors, clean cable connectors, keep everything in a safe, dry environment without oil. So how to clean sensor? You can use some non-woven textile and the spray. So here we have the non-woven textile and the cleaning spray. So this is the situation which not should remain. So this is the covering of the sensor by the grease is just only for the measurement purposes. After the measurement, you have to clean properly the membrane. Really use sufficient enough amounts of the cleaning spray, of the detergent to clean properly the sensor. Use some kind of non-woven textile to really clean the sensor membrane. And the same should be done even with the connector. Do never touch the sensor by dirty hands like this. Never ever. If happens, clean this connector. Use really good amount of the detergent. Use the non-woven textile and clean it properly to be really clean. Then use the cap and cover. Never use the sensor without the cap. Keep the connector all the time covered by the cap. Another example is this sensor. It's just after the test with the cap, and as soon as you finish the test, you remove the cable, immediately mount the cap. Now we have to clean the sensor. First, clean like this, check whether there is a sealing ring or not, and then remove the cap. Very easy. So this is the cap, and this is the sensor. Again, clean the membrane properly. You see second sealing ring. Clean it. Use piece of textile, and that's it. You can see here. Wait a little bit. Yeah, you can see here. Sensor is clean. Now we have to clean the connector. Again, use the detergent. Clean even the cap if it is not clean. Leave it a few seconds and then mount the cap. The same situation is with the cables. Never leave the cables like this. All the time use the protection. For the BNC connectors, same way for cleaning. Clean properly. Check visually whether it's clean or not. If it is clean, then use clean cap, put it on. Then the smaller connector, again, use sufficient amount of the detergent, clean it. Use clean cap. If you are not sure, you can clean it. And after a few seconds, you can put on it. And that's it. That's the way how to store your cables. So that's all from today's session. If you have any question, do not hesitate to ask. And thank you very much for your attention. If you have any questions, please use your question answer chat. If you have any question, if your questions are very difficult, you can send us an email and I will answer all your questions. Thank you and goodbye.